Okay, in this screencast, we're going to be looking at the effect of a nearby real pole on a second order step response. Okay, if you'll remember, we cared a lot about looking at a second order model for a system, and we assumed something like this, where we had omega n s squared plus 2 zeta omega n s plus omega n squared. And we knew what the step response looked like, and we could get ideas of what the pole locations effect on the step response would be. So, for example, if we knew omega n, we could get the rise time was about 1.8 over omega n. So we had some ideas of what was going to happen when we had a system that's well modeled by a second order transfer function. So the question becomes, what happens if this assumption is not really accurate? Okay, we talked about the idea of dominant poles, and the idea there was if you had, let's say, a pair of complex conjugate poles, and then you had other poles that were way off to the left, these would decay so fast that they wouldn't have much effect on the overall step response. Okay, but what happens when poles kind of get nearby, so to speak? All right, so let's take a look at how we would study that. Okay, so let me start this over. And I'm going to start by drawing a pair of complex poles. Okay. All right, and I'm going to say they're about right here, and the complex conjugate would be about right here. And you'll remember this radius is omega n, and then this line coming down is the real part of the complex pole, and that would be zeta omega n. Okay? So, if we were going to add a nearby zero, one thing we could do is come up with a different transfer function model. Okay, I'm going to call this one h1, so we can use that for comparison. We could have an h2, all right? And what I'm going to do at this point is to make things a little bit easier. The book talks about using normalized frequency and normalized time. That's one way of saying we could just let omega n equal 1 and sort of study the general effect based on one value of omega n. And it would give you an idea of what happens. And if you changed omega n, the result would happen faster, okay, if you made it bigger, okay? All right, so if we do that, if we substitute omega n equal 1, then what we would have here, if we had a nearby pole, we could, first of all, write down our complex conjugate pair. So this would be s squared plus 2 zeta s plus 1. Remember, omega n is equal to 1. Okay, and then we could model this as s over alpha zeta plus 1. Okay, that's a weird way of writing that, but let's see what that does. If I had s over alpha zeta plus 1, and I set that equal to 0 to find the pole location, that would mean that s over alpha zeta is equal to negative 1, and s is minus alpha zeta. Okay, so what that means is, if, for example, I let alpha equal 1, at alpha equal 1, we would have s equal minus zeta. Okay, so in this picture, that would be right here. All right? So what happens when alpha is equal to 2? When alpha is equal to 2, you would move this over to, I can't make that hang on. You would have to carefully erase that and move this over to alpha equal 2. All right, so you see, as you increase alpha, you move the pole location further and further away from the real part of the complex conjugate pair. All right, so we'd like to study that. We can make some plots as you change alpha, okay? And so what I want to do next is skip over to MATLAB and make some plots using this model. Okay, so I've set this up to do the plot we just had talked about in the previous section of this video. So what we're going to do is use several values of alpha. So we're going to start at, you see, 0.5, and then move up to 1, 2, 3, all the way up through 100, and take a look at what happens. For this particular case, we use a damping ratio of 0.4. All right, so I wanted to compare that to the case where there's not a pole. So we use the normal second order response. And so this is highlighted in blue, H1. And I need to put this up ahead. So that would go here. All right, so that makes this a transfer function object. All right, and so when I use the letter S, H1 is now a transfer function object. So I can use the step command on it. All right, so the step command lets you assign the output and the time scale that you're looking at. Okay, so y1 comma t and is the output of the step function. So I get both the y-axis and the time axis. Okay, so initially I'm going to plot. This would be the regular second order response with no interfering pole. All right, then I'm going to hold that plot and put this in a loop. All right, in this loop, we're looking at a nearby pole. All right, so remember, as alpha gets bigger, that nearby pole goes from, at alpha equal 1, it goes from sigma, and at alpha equal 2, it's moving away from the real part of the complex conjugate pair. All right, so from there, it takes the output of the step response and plots it. Okay, and then so that we can see this evolve over time, I have the program pause for 2 seconds so we can watch what happens with the plots. Okay, let's make it pause up here for longer than 2 seconds. Let's pause for like 4 seconds to get the plot up on the screen. All right, so we'll run this and let me move this over. So we see, here's the normal second order response. Here's alpha equal 1/2, alpha equal 1, alpha equal 2, 3, 4, and you see it's approaching it. Alpha equal 4, it starts to approach asymptotically the regular response of just a normal second order system. Obviously, by the time we get out to alpha equal 10 and 100, that's the complex conjugate pair is a dominant set of poles. All right, so what would you say happens? Well, if you have a nearby pole, it reduces the overshoot in fact, if you have alpha equal 1/2, you have no overshoot at all. You have an overdamp case. All right, as you increase alpha, the overshoot, is not as drastic, but yet the rise time starts to increase. Okay, so the system in some sense becomes slower. All right, so here's an example of how you would analyze the effect of a nearby pole. Let me stop this.